Hey everybody, so we're continuing with chapter 18, which is kind of talking about keto and enol tautomerism. That's sort of a main topic. You know, we have the two different forms of a ketone or aldehyde, and they are tautomers, right? And as I'll review from last time, but basically you can envision the two tautomeric forms, the keto tautomer and the enol tautomer, and they're in a rapid equilibrium between the two forms, catalyzed by acid or base. They're not resonance structures, right? Because you're actually rearranging the connectivity a bit. Here's the acid catalyzed mechanism of how that happens. With acid, you protonate the ketone or aldehyde, and then you make this protonated ketone or aldehyde intermediate, and then a mild base, usually water, comes and takes off that proton, and that makes the enol. So it can go back and forth. That's a very easy equilibrium mechanism. And generally speaking, the keto form is the favored one. So it'll, they're in equilibrium, but usually it's much more of this, much less of this, but they can go back and forth. And there's also a base catalyzed mechanism for this, where to go back and forth. And what happens is the base would just take the proton off, and then it creates a negatively charged oxygen, and then it gets a proton. So that's actually really easy as well. And as we were reviewing from last time, one of the things you can do with this reaction, and enols and ketos, is that you can halogenate, like alpha brominate a ketone or aldehyde. What does alpha mean? Alpha means like the carbon next door to a ketone or aldehyde. So alpha brominate, alpha halogenate, whatever. This is from last time also. I'm not going to review it all, but basically the ketone could react with Br2 and acid, like acetic acid, and then what it does is it provides one bromine at the alpha position. Okay, so it stops at one bromine. Mechanism is essentially ketone plus acid makes the enol, and then the enol is nucleophilic, so the oxygen swings down, alkene attacks, then you get this intermediate with the extra proton, lose the proton, and you're done. So that's how the alpha halogenation worked. And the other thing is, if you don't use acid for the reaction but you use base instead, there is it kind of changes the mechanism a little bit in a way that first you get one chlorine, and then it kind of continues, and then it'll exhaustively chlorinate or brominate, depending on what you're using, the alpha positions. Okay, so when you use base mediated, it's exhaustive. But when you use the acid catalyzed reaction, only one halogen gets inserted. We showed how the mechanism kind of shows that. You can review this discussion from the notes last time. The main thing is that when we use base and then a chlorine gets incorporated, and then it takes off a second proton, this intermediate is kind of stabilized because you have a negative charge next to the chlorine. It's a stabilized intermediate, and then basically, since it's stabilized, then that enolate is ready to go attack again, rather than get stuck at the monochloro. It just keeps going. So first you get monochloro, then you get, after this attacks, you get dichloro, then it attacks the other side, and you get trichloro, then you get tetrachloro. We're not showing all of that, but the main thing though is if you use the base mediated reaction, you get exhaustive halogenation. And I think the last thing we mentioned last time is that if you sometimes you want to actually turn a ketone into this thing called an enone, which has a ketone next to an alkene. Enone, get it? The way you do that is you do a monobromination with Br2 acetic acid at the alpha position, and then we use a base, usually it's pyridine, and that rips off the next door proton, kind of like an E2 reaction, and then you get an alkene. Why does this matter? Well, you'll see very soon that we can add nucleophiles to this alkene position, and that makes it really cool because it gives us a way to attach stuff right there at that position. This position is electrophilic, so we can add nucleophiles there. All right. Okay, so we're moving forward now. Now we're on to number 4, which is another reaction where we use these sort of enolate type intermediates as nucleophiles, so they're going to attack stuff. And here we're going to talk about alkylation of aldehydes and ketones. Alkylation of aldehydes and ketones. So what does alkylation mean? It means attachment of an alkyl group, like a methyl or something, right? And this is an SN2 reaction, so it's kind of based on your organic 1 knowledge a little bit. And there is, so we're basically, we'll draw it out in a second, we're going to take a ketone or aldehyde and make an enolate, right, with a strong base, and then we're going to attack something, and that's going to do the SN2 reaction. The things we're going to attack are typically methyl or primary, so like methyl iodide or aldol bromides. That's a methyl, that's a primary. What about some other primary ones you could attack? That's a primary one also. So yeah, these are primary. This is methyl. Okay, but not secondary or tertiary usually. So not secondary or tertiary, because those will cause, usually they cause elimination. They cause the E2 reaction, which is from also something from organic 1 a little bit. So secondary and tertiary are more likely to give you an E2 reaction. Primary or methyl are usually to give you a clean SN2 reaction, substitution. Okay, so let's show a couple examples. First example, I'm going to just say direct alkylation. Direct alkylation basically is going to mean let's make a nucleophile from a ketone or aldehyde and then directly alkylate it. So that seems great. Why don't we do it? So we'll take cyclohexanone, and we're going to react with a super base and then an alkyl halide, and that should, let's just pretend we're going to attach that nice primary alkyl group, maybe from aldol bromide there. Alright, and what are the two things we need? Well, first we need to take off the proton with a super base, and then we're going to attack with an alkyl halide. So, like this primary bromide, which is, I just showed it up here also. Yeah, and it has an alkene in it, but that's irrelevant, right? Okay, so what's the base we're going to use? Do you remember what the super bases are in this chapter? It's a 3-letter base. It's LDA. That's a very common base used to deprotonate ketones, aldehydes, esters, nitriles, all sorts of things. This will rip off this proton because it's a super strong base. It'll rip off that somewhat acidic proton. I'll just draw a mechanism like B dot dot is the base. That's what LDA is. Base takes proton. It makes the enolate. Okay. Enolate's a nucleophile, that's an electrophile. What's the structure of LDA? Let's just draw it over here. LDA nitrogen, isopropyl, isopropyl, dot, 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 dot. So there's 2 lone pairs, dot, dot, negative, lithium plus. So that's what LDA is. It's a very, very strong base because of the N minus, right? Okay, so anyway, B dot dot abbreviates that. Base takes proton, makes an enolate. Why is it not an enol? What's the difference between an enolate and an enol? Well, an enol has a proton because it's an ene alcohol, right? Enolates are the ones that are negatively charged. Okay, it's a good nucleophile. That's a good electrophile. How do I draw the mechanism where this carbon gets attached? Well, what happens is the oxygen swings down and the double bond attacks. And now we got our product. So that's actually, it looks very nice and easy, right? This is a way you can almost take any ketone or aldehyde and attach something next door, like a allyl group or whatever, okay? Alright, so it looks so nice, but there is a problem. The problem is called overalkylation. And that just means, yeah, you might attach one thing, but it may keep going. And what I mean by that is you may get maybe some of this. It might attach one side, it might attach the other side. It might also even make a little bit of this. It may make a little bit of mono substituted, a little bit of di substituted, it may make some tri substituted. So when you make mixtures of products, that's usually a problem. So the problem is overalkylation and making mixtures of products. And so therefore we usually say it's a low yield reaction. There are some times it works great. So I'm going to say, like, in certain cases it works fine. I think, like, with this kind of ketone where you have both 2 sides of the ketone, that actually maybe makes it more likely to accidentally attach it to both sides. In certain cases, it's less of a problem, we'll say. So, for example, if I have a ketone with one side, like this ketone next to a benzene, and I do like LDA, and we'll do the same alkyl halide. You know, you still have 3 possible positions here because it's a CH3, but since there's not 2 sides to the ketone, you're maybe a little more likely to just get what you want, which is that, like a mono substituted. Okay. Anyway, so yeah, that's what we mean by direct alkylation. Sometimes it works. Sometimes you get a little bit of a mixture. Sometimes it actually works fine, but you may get a little bit of the di-substituted product where you have a second allyl group at that position, right? A second allyl. But we'll say certain cases can be okay. But there's an improvement, and that's why I want to mention. First, we mention this sort of direct method, and then we'll mention a method to improve it a little bit. Alright, so we mentioned, we're talking about alkylation of ketones and aldehydes. We mentioned direct alkylation. Let's talk about a slightly indirect method that solves this problem of accidental, like, dialkylation or trialkylation. And this is method B. And this we're going to call alkylation by enamines. Oh crap, what's an enamine? Do you remember what enamines are? It's one of these things that we have to kind of remember from your previous organic knowledge. Okay, enamines. En means maybe alkene, amine means an amine. So it's going to be functional group we just learned about in the last chapter, enamines. This gives monoalkylation. And that's why it's kind of cool. It avoids all the dialkylation and trialkylation stuff. All right, so what is it, and what's the method? All right, so let's just show a ketone, and think about what do you get when you react this ketone with an amine, a secondary amine. A little bit of acid, catalytic acid, H+. Remember what we did last chapter when ketones or aldehydes react with a secondary amine? It makes something. Do you remember what it makes? So amines are nucleophiles, and they attack the ketone, and it makes this thing called an enamine. Remember that now? Alright, we'll review the mechanism in a second of how this works. It's called enamine. Right? There's a ketone and we make an enamine. This turns out to be a good nucleophile. So being a good nucleophile, we can alkylate stuff. It's kind of like an enol or an enolate, right? And it is a nucleophile. What is the ketone? Was that a nucleophile or an electrophile? Because remember, what happens is the nitrogen attacks the ketone. The acid helps out also. But basically speaking, this is an electrophile. This is an electrophile. So we converted an electrophile into a nucleophile. And the nucleophile now reacts with, let's just pick a alkyl halide, like benzyl bromide. It's a nucleophile. It's going to attack that carbon and kick off the Br. Okay, and so being kind of like an enolate, the nitrogen actually swings down, and the double bond attacks the carbon and kicks off the Br, and gives you now we have a double bond to nitrogen, right? And we have our thing that we just attached. Any charges? Am I missing any charges here? Is that a normal neutral molecule? Well, nitrogen bound to four things is always positive, negative, neutral. What is it? It's positive, right? It's a positively charged nitrogen now. Okay? This actually has a name also. You have to remember what the name is. If you go back to the last chapter, we were talking about all these things. We have enamines. We also have, maybe I'll just draw one over here, just for naming. Okay, I have that. What's that called? That's an enamine. This is not an enamine. This is an imine. Carbon double bond nitrogen, that's an imine. Well, this is not an imine. It looks like an imine, kind of, but it's got the positive charge. So this is imine, this is iminium. Okay, cool. The big thing is this is not a nucleophile, because if this was a nucleophile, it might react a second time. It's actually an electrophile, so, but it stops reacting. There's not, you know, assuming we have a bunch of this stuff around, this isn't going to react with it anymore because it's actually an electrophile. Things attack iminiums, while enamines are actually nucleophiles and they attack things themselves. Okay? So I'm going to have to show I'll show the mechanism of how we finish off the reaction. But basically water just cleaves off the nitrogen and you get our nice monoalkyl product. See what we got? We have a clean product. This net process took a ketone and made the enamine, attacked something, and then cleave the aminium off to give us back our ketone, right? Like, could we do this somehow in a single step, like from there to there? We do LDA, right? LDA and then that benzyl bromide. That would actually do it, except you might get multiple alkylations, and that's why this is a better method, a improved method. Okay. Let's see. Oh yeah, what? Maybe there's like, what are the mechanisms here? I mean, it's a bunch of stuff's going on. Where was this mechanism? Where was this mechanism? You learned this. This was in what chapter? It was the last chapter, chapter 17. Okay. I'm probably not going to show it because you should be able to do this. Go look in your chapter 17 notes and try to do this mechanism. If you get stuck, come to office hours, right? The basic gist of this, you know, chapter 17 was all about things adding to ketones and aldehydes. The mechanism was the ketone would get protonated, right? You activate the ketone, and then the nitrogen would attack, and then you do proton transfer, kick off a leaving group, etc. But look in your chapter 17 notes for how to do an enamine, ketone to an enamine. All right. I would actually recommend in your notes around this section practice that mechanism just to review this, because this might all be on a quiz. I might give you a whole quiz question that's like, draw the full mechanism from here to here plus there to there. That's easy, right? I'll show, and then there's a last mechanism of like how water cleaves this off. I'll show you that in a second because you've never learned that mechanism. Okay, but here to here is like a, you know, 5-6 step mechanism. This part's really easy. The enamine attacks, kicks off the BR. Now you have an aminium, which is an electrophile, and water will attack this and then give us this. That could be a big, long, fun mechanism on a quiz. All right. So let's show the cleavage mechanism right now. Aminium cleavage mechanism. Aminium cleavage reaction mechanism. Okay, so there's our aminium. Let's throw in some water. Out comes the ketone. And you get the top part is the amine that's kicked out. All right. So how does this work? This is an electrophile. That's a nucleophile. What's going to happen? This just attacks. All right. And what does that give us? This kind of mechanism is sort of what we were seeing in chapter 17, the last chapter. All right. What's the charge? Well, water gave up its electrons. It's positive. All right. What were we always doing after nucleophilic attack? Last chapter. You always do nucleophilic attack, and then you have something positively charged, and we always did something afterwards. It's 2 letters. It's PT, proton transfer, from oxygen to nitrogen, because nitrogen's got to go. It's coming off as a leaving group. So we're going to make nitrogen a better leaving group. Proton transfer does that. Okay, so now we have OH. Now we got nitrogen, proton. Okay. Now we got a good leaving group. So oxygen kicks off the good leaving group. Nitrogen goes away. Okay, and how do you think we finish off the mechanism to give the product? do we do? How do we finish off the mechanism? All we got to do is remove a proton. So just write -H plus. Cool. That's it. All right. Here's another example of this process. And you know, the name of this whole process is monoalkylation, which just means attachment of a single alkyl group. Monoalkylation of enamines. Let's just try, I don't know, what do you think? So to make an enamine, let's go back to the last thing we were just talking about. What are the things, like what kind of amines react with ketones to make enamines? What kind of amine is that? Well, how many R groups are on the amine? Is it a primary amine or a secondary amine or tertiary amine? Well, that is a secondary amine because there's kind of like 2 R groups, even though it's all cyclic. That's a secondary amine. Secondary amines make enamines. Primary amines make imines. Okay, primary amines make imines, secondary amines make enamines. So that's all last chapter. Alright, cool. So let's just consider another example where we're going to make an enamine, alkylate it, and hydrolyze it. And just try maybe, I don't know, let's do that. Alright? Let's think about this. Well, for what's the hydrolysis step? That was really easy. Number 3 is like you have an iminium and you hydrolyze it with what? Water. Okay. What's the alkyl halide? Assuming we make an enamine, make a nucleophilic enamine, we throw in an alkyl halide for number 2. What's the alkyl halide going to look like? It's going to look like that with a bromine or something on it, right? That's a primary alkyl halide. So isobutyl bromide. Okay. Now for fun, what enamine did we make last time? It was that with that 5-member ring nitrogen thing. But we don't have to use that. We can use any secondary amine. So this would, and then a little bit of acid cat, H plus cat. This is diethylamine. Well, it makes enamines too, right? All right. This is a big long mechanism, and you should practice this. I'm not going to do this mechanism for you. You're going to have to review how to make an enamine. How to make an enamine, right? That was in chapter 17. And then the attack of the enamine onto the alkyl halide. That's really easy. It's one step. And then the hydrolysis, right? I'll just draw what the enamine looks like. That's the enamine, right? This diethylamine reacts, makes this enamine. Okay. Anyway, so what I'm going to do is just say, like, for you to practice, maybe for a quiz, do every step of this mechanism. See if you can do it. Do the formation, practice every step. Practice the formation of the enamine from here to there. Look it up, chapter 17. Practice the attack of the enamine onto the alkyl halide. Maybe I'll just draw that intermediate for you. It's the iminium, right? Plus charge on nitrogen. Okay, and then the hydrolysis, which water attacks. We just showed you that. Yeah, see if you can do this. Practice every step. I want to say, I don't know the exact number of steps. It's probably something like 15-step mechanism. something, I don't know, something like that. See if you can do every step of this. If you can, you're doing pretty good for that next quiz. All right, 15 step. I don't know if it's 15 steps. It feels like 15 steps. It might be 10 steps. I'm not sure. Okay, cool. So practice that for more practice. Okay, number 5. Moving on to some more fun stuff in this chapter. This is a reaction called the Aldol condensation. And like a lot of these new topics, you're going to see these until the end of the course, so you really got to learn them well. So I'll say a little star or whatever. This is one of the really important organic 2 reactions. It's called the Aldol condensation. Aldol, what does that mean? It is going to be, basically what it means is reacting a ketone or aldehyde with itself. Reacting ketone or aldehyde with itself. And it kind of doubles the size of it, or if we have a 3-carbon thing, it becomes 6 carbons or something like that. Let's show a basic idea, and then we're going to have to just go through some of the different variations of it. Alright, so the basic idea, in a nutshell, is this. The basic idea of the Aldol condensation is, if I take acetone, I can demonstrate this. Alright, so treating this with a base, so it creates an unfavored equilibrium, a disfavored equilibrium, so it's actually left favored, which is kind of weird. Treating this with sodium hydroxide, NaOH, which is a base, and like water maybe, or maybe some methanol, but it's just a basic mixture. We'll create something that looks like this. Okay, I'll show the mechanism of this. It's really easy. Alright, and this thing has a name. Of course, what's the name of this? This is acetone. It's a ketone, right? This thing has a... what are the positions called? This is the alpha position, that's the beta position. This is the alpha, and this is the beta, relative to the ketone, right? Alpha, beta. Okay. So this thing is a ketone with a, what is that thing at the beta position? What's it called? It's a alcohol, right? That's an alcohol at the beta position. We also call alcohols hydroxy groups, so that's a hydroxy that's beta to the ketone. And so we give this thing a name. It's called a beta hydroxy ketone. Beta hydroxy ketone. Beta hydroxy ketone, right? All aldol reactions, aldol condensation, all of them start by creation of something called a beta hydroxy ketone. It's a hydroxy at the beta position, all right? And then what happens is that this thing, when you heat it, and usually you do the whole reaction under heat, so it's like you actually do apply heat overall, but the second step of this is going to be water getting kind of kicked out of this. So water is going to go away, H2O. And you're going to make a different product. And this is the final product of an aldol reaction, which is a ketone next to an alkene, and there's like paramethyl groups there. All right. Is this still a beta hydroxy ketone? No, there's no more beta hydroxy, right? There's a name for this thing, which we still have our alpha and the beta positions, alpha and beta, right? How do we describe an alkene in between the alpha and the beta positions? You might say, it's a alkene, ketone with an alkene in the alpha and beta positions. But we have a better name for that. It's called an alpha, beta, unsaturated. So unsaturated means alkene, right? Alpha beta unsaturated ketone. Okay. Alright, so every aldol reaction will kind of start by making a beta hydroxy ketone, and then with lots of water, you create an alpha beta unsaturated ketone. Sometimes it'll be an alpha beta unsaturated aldehyde. Yeah. Alright, so what's the mechanism of these steps? It's actually pretty straightforward. The mechanism of the first part is you got a proton, and I'm going to, yeah, let's just draw me equilibrium. Here we go. So we have OH minus, OH minus. What's one of the themes of this chapter is that we can take off the neighboring proton next to a ketone or aldehyde and make a enolate, right? And enolates are nucleophilic. So this base takes off the proton, and I'm just going to go straight to the enolate. That's the enolate, right? Enolate. We know that enolates are nucleophilic or electrophilic. Enolates, I mean, it's got a negative charge. Usually negatively charged things are nucleophilic, right? So now it's going to react with more of the acetone. And that's funny because we're taking a ketone, which is actually an electrophile, right? Things attack ketones. We're turning a ketone into a nucleophile. We're turning an electrophile type thing into a nucleophile. Enolates are nucleophilic. Nucleophile, right? And we're going to react it with more acetone, which is an electrophile. That's basically it, E+, right? This thing is a nucleophile, that thing is an electrophile. So how does it all work? So this just now, it'll take one of the lone pairs, swing down, make a double bond. I'm going to redraw this slightly larger at the bottom. Okay, there we go. Nice. So now the enolate nucleophile, electrons swing down, the double bond goes and attacks the ketone, because we have a bunch of acetone around, right? So even though we just say, acetone there, we have a lot of acetone. So some of it gets turned into nucleophile, attacks acetone as an electrophile, and that creates what? It creates that. And how do we finish off this mechanism? And what I'm trying to show is each step of this is in equilibrium, right? But the overall equilibrium is actually favored on the left. So it's a little surprising that this even works, because it's kind of favored on the left. We'll come back to that topic in a second, all right? But mechanistically, yeah, it's reversible, 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 all right? How do we go from O minus to OH? And we have water around. What do you think? H2. How do we go from O minus to OH? Well, this just grabs a proton from water. Cool. All right. And that's how we get to the beta hydroxy ketone. That's pretty straightforward. All right. I want to show you the second step of this. I'm going to do it underneath because we're a little out of space over here. Okay, but let's go back. Let's go back to the topic of, why does this even work at all if we have a disfavorable initial step? The reason is because once this forms, it has an irreversible step to make the final product. This thing is actually very stable, and so even if this is initially disfavored, it doesn't mean it's completely disfavored. Once you make some of it, it actually continues on to form a very, very stable final product. Okay, so we'll talk about that a little bit more. All right, but this is this is an example of, if I have like A and it's disfavored to make B, and then irreversible to make C. Where does this equilibrium going to lie? It's disfavored to make B, but still a little bit of B forms. And then once B forms, it totally forms C irreversibly. What's the major product of this? It's going to be C, right? C is the favored final product because irreversible initial equilibrium will continue to a reversible initial equilibrium that has a follow-up irreversible step, like it's irreversible, right, to make a very stable product. Yeah, this will all completely go to C because this is irreversible, right? All right. So what I need to do is show you the mechanism from the beta hydroxy ketone to the alpha beta unsaturated ketone, and I don't really have space here, so I'm going to do it underneath. So I'm going to just write mechanism second step. Mechanism and there's also another name for this. I mean, what are we losing? We're losing water, right? So another name for this is dehydration. Dehydration. Because we're dehydrating it, all right? Where is the water coming from that we're forming? We're forming H2O. So while there's the O, there's an H. Where's the other H? And of course, this is a CH2 and that's a CH, right? CH2, CH. So the water is coming from OH and then actually this alpha proton. So you're losing an alpha H, you're losing an alpha H, it's going from CH2 to CH, and you're losing the beta hydroxy group. That's how water is being formed. Okay, so let's show that all as a mechanism. It's a pretty easy mechanism. I'm going to redraw the molecule above. So I'm going to show that alpha proton now. Heat, water goes away. Especially if you go above the boiling point of water, well then not only does it go away, it vaporizes, right? Alright, what are we calling these things? This is a beta hydroxy ketone. Beta hydroxy ketone. And the product is the alpha beta unsaturated ketone. Okay, cool. So, how does this mechanism work? So, the way the book shows it, and I'm just going to follow that mechanism. We still got base around, right? We have sodium hydroxide, we have a lot of base. And what do bases do? If you have a ketone with that somewhat acidic proton next door, well, the base takes the proton, makes an enolate. It's just like how we started the reaction, right? Just like we started with acetone. Base takes proton, makes an enolate. So base took a proton. Now we get an enolate. And the enolate now, rather than be a nucleophile, it's going to swing down and kick off OH. That's it. That's all there is to it. That's actually a pretty easy mechanism of how the enolate swings down and takes off OH. Alright. Okay. So that's actually, that mechanism's not that hard. I could have probably snuck it up there, but you should continue this. Consider this a two-part mechanism. The first step gets you to the beta hydroxy ketone, and the second step is this this dehydration process with just base. Form an enolate, kick off OH. All right. So, a couple questions here. We'll kind of address them each. First question is, why is that equilibrium initially disfavorable? First question, why is the equilibrium disfavorable? And that, what I mean by that is up top here. Why was this disfavorable? It's like, why is it not want to go to the beta hydroxy ketone? Do you have any ideas on that? Like, why might it not want to go here, right? Why is the initial equilibrium disfavorable? Probably due to sterics. Probably due to sterics. Because you got a lot of stuff going on up there, and you know, the intermediate has a hydroxy group. You have the two methyls. There's a lot of like things potentially bumping into each other. So the ketone might bump into the OH. It's kind of maybe a sterically hindered intermediate. So why is the equilibrium disfavorable? Probably due to sterics. And the other thing is, why is the final product so stable? Why is final product so stable? And like this shows the very final product, right? The alpha, beta, unsaturated ketone. Why is it so stable? So probably two reasons. It's less hindered. That's one. I think the more important thing, though, is not the hindrance. It's the conjugation, which between the ketone and the alkene. Like you have two functional groups that are next door to each other, right? And that's a favorable interaction, right? So it's less hindered and it's conjugated. That's the word we use. Conjugated. Okay. And that is stabilized by resonance. Okay, so we'll come back to that a lot. Stabilized by resonance. When you have a ketone next to an alkene, that's actually a resonance stabilized functional group, because you can push the alkene towards the ketone and we can draw that. Let's draw it real quick. Okay, let's draw the resonance stabilization of the product. So it's, and when we can draw resonance, that indicates stability, right? So that has resonance stabilization, so I can push the alkene towards the ketone into our resonance structure. That's a huge deal in terms of the stability of the molecule. That single resonance structure makes it really happy. Okay, so why is the product so stable? For one, it's less hindered. It's also conjugated, and it's stabilized by resonance. All right. One more question. Why is OH a good leaving group? Why is OH a good leaving group? That sounds crazy. Because we've always said that OH is a terrible leaving group, right? What am I talking about? Where's OH a good leaving group? that was right here. It's like, you know, I'm showing O minus swings down, kicks off OH as a leaving group, right? So why is OH a good leaving group? The reason is because the product is so stable. Because product is so stable. That's a pretty easy explanation. We're forming a very, very, very stable product. And that's why it's okay for OH to be, actually, yeah. You know, OH is typically a bad leaving group, but we're saying, oh yeah, here it's actually a good leaving group, right? And the reason is because the product is so stable. Let me just say that, let's just draw, you know, one more simple example. Like if I have a OH and I throw in a nucleophile, let's go back to organic 1, right? We say, okay, there's the product, right? Like, is this an okay reaction? The answer is no. This is a terrible reaction. This will not work. SN2 reaction will not work. This is an SN2 reaction, right? This will not work because OH is a bad leaving group. You need you need this thing to be a good leaving group for this to work. But the reason this is different here, why does this work with OH being a leaving group? And it's because of the incredible product stability of the alpha, beta, and saturated ketone. All right. Okay, so there we go. That's an introduction to the aldol. Now we have some little tidbits to talk about the aldol. Okay, so let's show another example of this aldol reaction. We'll just kind of focus on the product of it all. And we're going to use an aldehyde this time. So rather than ketone, let's try an aldehyde. It does the same thing, same mechanism, same everything. So 1, 2, 3, 4, 5. All right. So how many carbons? It's 5 carbons. 1, 2, 3, 4, 5. And I'll even write C5 up top. It's like 5 carbons. And when this aldols itself, what's the molecular weight? What's the carbon count of the product? It's 5 here. What's 5 times 2? It's 10, right? So NaOH, water. Okay. So whatever this, if this is 5, this is going to be 10. I'm going to draw the intermediate here in brackets because it's the beta hydroxy aldehyde in this case. Alright, and then kind of heat, we'll push it over to the final product. So, and it's also going to be C10. Alright, so what's the structure of the beta hydroxy aldehyde? Beta hydroxy aldehyde in this case, because we're talking about aldehydes. And what's the structure of the alpha beta unsaturated aldehyde? Final product. What are the structures of those two things? Okay. So to draw the beta hydroxyaldehyde, and we're not caring about the mechanism this second, just redraw this. Start with this. It's the same thing, but there's more. There's our C5, sorry, C5 plus 5 will be 10. So how do I draw the beta hydroxy aldehyde of this? So it's basically attached with another version of itself, and that's down here, OH, 1, 2, 3, I think it should be 5, 1, 2, 3, 4, 5. Okay. Alright. So, is this 10? Should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's good. Is it beta hydroxy? I'll clean it up a bit. There's the OH, right? There's the beta hydroxy next to the aldehyde. All right, and then what's the final product going to look like? It's an alpha beta unsaturated aldehyde, right? So it's going to have an alkene between the alpha and the beta positions. Sometimes, and this is not an acceptable mechanism, but it allows you to see the product. I kind of show that alpha proton and the beta hydroxy. This is not a mechanism, and if I ask you for the mechanism, you can't just do this, because, well, you can do this, but you need to show the mechanism also. But we can go like bloop, it just goes away. Like that's the water. That's the water that comes off, right? That's the water that gets kicked off. Right? There's the water, H2O there. Alpha beta. There's the water, right? Because the second step is water being lost. And what gets replaced where the water gets lost? An alkene. So the final product is going to be an alkene between those two positions. So it's going to look exactly the same, except now we have an alkene there. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's C10, right? C10. Okay, now does it look funny that I kind of flopped over this from the right side to the left side? Well, there's probably a mixture of alkene isomers, because the alkene could be the one way, or it could go the other way. So I'm just going to write E and Z. You might have a mixture, most likely we'll have a mixture of E and Z alkene isomers. Not that big of a deal. Most likely this is the stable one, because this stuff is farther away from the other alkyl stuff. But let's check the C10 one more time. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Very nice. Okay. So by E and Z, what's the alternate isomer? It would be this, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It'd be something like that. When I ask you for the product, just draw one of them. I'm not really rehashing the chapter, 12, the alkene stuff, in terms of alkene stability. So just draw one of the two alkene isomers, and that should be fine if I asked you. Or you can always ask me during the quiz, like, should I draw both of them? Should I draw one of them? I'm usually pretty clear about that. All right, so I'm going to put this one in parentheses. I'm not trying to emphasize alkene isomerism here. Most likely both of these are formed. Anyway, for practice of the mechanism, I would recommend you draw out the full mechanism. See if you can do it. From here to there, and then mechanism from there to there. This last, actually both parts are pretty easy, right? Base takes proton, makes an enolate. Enolate attacks aldehyde, and then you just get a proton to give you the beta hydroxy group. And then the second thing is that mechanism where base takes off the alpha proton, makes an enolate, aldehyde enolate, and then the aldehyde enolate swings down and kicks off the OH. Okay, so see if you can do this whole mechanism. That's a good practice problem. All right. Oh yeah, another thing about this example. With ketones, I was showing this initial equilibrium kind of being disfavored, right? It was sort of like kind of favored on the left side. With aldehydes, it's not necessarily that case, because it's less sterically hindered, right? This thing's not as sterically hindered because you don't have a second R group here, you don't have a second R group there. So this intermediate's a little better behaved. Nevertheless, in this course, we always assume that in an aldol reaction, this is a total aldol reaction, is that you first go to the beta hydroxy ketone or aldehyde, and then it always goes to the final product. In certain situations, this can be actually isolated. You can actually isolate these beta hydroxy aldehydes and stuff. Like this one might be isolable because it's actually a little more stable than the last one we showed, right? But when I ask you for a product, you just always assume first step, second step, all right? And sometimes on a quiz, I'll actually ask you first, first draw this and then draw that. So you draw them both as separate things, okay? All right, great. Okay, now we're going to do a little twist on the aldol. You guys, got the basic idea of the aldol. So this is called a crossed aldol. Sometimes people call it a mixed aldol. Okay, so all this means is it's going to be a slight twist on the aldol concept, where it's an aldol between two different carbonyl compounds. Okay, so let's just show an example. I'm actually going to show I'm going to call this a bad example too. So we'll talk about bad examples and we'll talk about good examples. So the bad example is as follows. Let's imagine we're doing kind of an aldol, and we'll use C2. So this is acetaldehyde. Right, it's two carbons. I'm going to call this A. And just for fun, let's make it react with C3, which is propanaldehyde, and that's B. Okay, and we're just going to use NaOH water, which is the typical reagent we use for aldols. And then let's draw the different products that are formed. And we're going to assume that it goes all the way to the end. So we're not going to show the beta hydroxyaldehydes. We're just going to show the alpha, beta, unsaturated aldehydes. So those alkene products, right? All right. So the first one, I mean, the thing about this is there's different combinations of these, right? A could be a nucleophile, A could be an electrophile. A could be a nucleophile, B could be an electrophile. B could be a nucleophile with A being an electrophile, or B could be a nucleophile and B could be an electrophile. So there's four combinations of products, right? I'm going to call them AA, AB, BA, and BB. Okay? There's four combinations. So the first one is going to be basically 2 plus 2 is 4. So it's this react with itself. So I'm going to call that AA. I'm going to redraw it a little bit to the left also. One, two, three, four. AA. Alright, so 2 plus 2, 2 plus 2 is 4, and that's A being nucleophile and A being an electrophile. What if A is a nucleophile, so meaning the alpha carbon of A is a nucleophile, and it reacts with B as an electrophile? Well, I'm going to call that A-B. And what's the structure of the product? Okay, so it should be 2 plus 3 should be 5, right? 1, 2, 3, 4, 5. Good. Okay. And what if B was a nucleophile and it reacted with A as an electrophile? It's going to look very similar to AA, but the name is going to be BA. And the structure is going to be almost the same. So draw the structure of AA. But what's the difference going to be? It has to be 5 carbons, right? If that's a nucleophile and that's an electrophile. So I'm just going to draw it the same way, but have a methyl right there. And that's what I'm calling BA. So it's 1, 2, 3, 4, 5. Let's draw the alkene a little more clearly. One, 2, 3, 4, 5. Okay, that's BA. What's a BB going to look like? Well, BB is going to be kind of like BA meets AB. So it's kind of like a combination of those two structures. This should be how many carbons? 3 plus 3 should give 6, so it's 1, 2, 3, 4, 5, 6. Very nice. So that's the structure of BB. Okay, so this is a bad example. Why is this such a bad example? Because generally speaking, as organic chemists, we really don't like making mixtures of 4 compounds. It's like when you do a reaction, A plus B, you want C, right? You want one product. You know, you never desire a mixture of 4 products, right? That's usually not what you want. That's why it's a bad example. All right, so the problem here is there's no preference. Four products are formed, and that's usually undesired, right? So what's the good example is going to be versions of this reaction where we might be able to get a single product out. Like that's what we want. Organic chemists always want a single product. We don't want 4 products. Okay, so let's talk about ways to maybe prevent 4 products from forming. Okay. Okay, so let's show now a couple good examples, or another way to say that is better examples. So there are improvements on those mixed aldol reactions we were just talking about. So the main difference with these, and like how are we going to accomplish a more clean mixed aldol reaction, is we're going to require one side of the, one of those components, so one of the ketones or aldehydes or whatever, one component to have no enolizable CH. So it will not have an enolizable CH. And by that we mean certain aldehydes work really well as a mixed aldol component. So certain aldehydes. No enolizable CH. What do I mean by that? All right. So let's just think of like benzaldehyde, right? Could this be a nucleophile in an aldol reaction? Could it be a nucleophile? The answer is no, because there's no enolizable CHs, right? This isn't you have a CH there, but that's not relevant. You need an alpha CH to form an enolate, right? There's an alpha position, but there's no CHs right there. That is, so this could not be a nucleophile. This could not be an enolate, right? So this is an electrophile only. Can only be electrophile. Can only be an electrophile, right? It can only be an electrophile. And that simplifies this a bit. Because if one of the components can only be an electrophile, then it can't be a nucleophile. If it can't be a nucleophile, it's going to eliminate some of those bad mixed aldol products. So let's draw another one. Let's think about it like this aldehyde. As an aldol electrophile, we'll say it's because this could be an electrophile. This could also be an electrophile, right? Because it's got an aldehyde, can be attacked. But does it have any alpha CHs? No, those are methyls, right? Those are all 3 alpha methyl groups. So this can also only be an electrophile. Also, only an electrophile. So these kind of things will help avoid all those many mixed aldol products. Okay, so I'll just show you a couple examples now. These are two examples. So if I have like this is one of the ones I just drew, this trimethyl acetaldehyde. And we'll throw in maybe this as a nucleophile, right? So this is a electrophile. This will be the nucleophile, all right? And it can also be an electrophile itself, but we're going to have a strategy to avoid that. If all goes well, this will be a nice nucleophile, that'll be a nice electrophile, and they're just going to attach. Okay, so the reagent is NaOH, water. NaOH, water. The basic idea of the mechanism is that will be a nucleophile, the alpha carbon, and it will attack, right? So I'm gonna, that's not a full mechanism, I'm just showing like, okay, well, assuming that we form an enolate, and the enolate has resonance, that's a negative charge, it's carbon with a negative in resonance. This attacks, right? What's the product? And first you make the beta hydroxy aldehyde, right? So it's 3 carbons, 1, 2, 3. There's 1, 2, 3, and then this is 1, 2, 3, 4, 5. 5 carbons. So it should be 3 plus 5 is 8. Let's see, is it 8? 1, 2, 3, 4, 5, 6, 7, 8. Got our 8 carbons. There's our intermediate, and what's the product? With heat, lots of water, it'll form an alkene between these two positions. And I'll do our little memory aid. So there's the water that's going away, right? And the product is this. Very nice, right? So that's the nice product. One more trick. I was mentioning like this could be a nucleophile, but it could also be an electrophile on itself. How could we avoid it being an electrophile and just being a nucleophile? And the trick we can do is we can add it slowly. Add it slowly. Okay. By adding it slowly, what is the effect, right? We have this mixture, we add this stuff really slowly. So the concentration of this is very low, right? Concentration of this is very low. And when it gets added, it reacts with the base, makes the enolate, attacks this because there's a lot of it around, right? And then it does its aldol stuff, right? So by adding it slowly, this prevents that self-aldol of itself. This prevents it from being a nucleophile and reacting with itself. So this prevents self-aldol. So that's one of the little tricks we can use. What are the 2 tricks? One trick is use something that can only be an electrophile. this can only be an electrophile. The other trick is add the nucleophile slowly. Add the nucleophile slowly. It prevents the self-aldol business. You get a clean product, and that's an example of a good example of an aldol. Okay? Alright. I'm just going to draw one last one and we're done. So, one more ketone benzaldehyde, which we already said was a really good one. NaOH, H2O. Beautiful mixed aldol product. We'll talk about it next time again, but this is the same principle. And which one of these do we add slowly? The nucleophile, which is attacking. You know, that's roughly the mechanism, right? And yeah, that's the thing we add slowly. Add the nucleophile slowly. Add slowly. And it's a beautiful example of a mixed aldol. Alright, we're done.